Hi, my name is Charles. I'm a data scientist at AWS, and I've been working here for almost 3 years. I help customers to formulate their business problems into machine learning questions that can harness the power of AWS. I specialize in reinforcement learning, which is a special branch of machine learning. This is when an agent or machine interacts with its environment, performs actions, and learns by trial and error, in contrast with supervised learning, which is an offline learning method with a completely labeled dataset. For those of you who've heard of RL's success with gaming, I've got news for you. RL isn't just for games. Customers all over the world are using RL to optimize day-to-day decisions that they make. I love reinforcement learning because it recommends a more optimal action in a business context every time it gets feedback. I've been putting reinforcement learning into production globally, and I'm here to show you how to get started. Reinforcement learning is a way of defining a problem where you optimize the action that you do now to get a better future reward. The formulation of the problem is crucial in the success of its application. Once you have the problem decomposed into a sequence of steps, execution becomes more or less a mechanical process. You can then choose the algorithms and tooling that AWS offers on the SageMaker RL stack. After deploying RL numerous times, I wanted to give you my workflow for deploying RL in practice. We will build up to this by asking 3 questions and working over a few relevant practice use cases. The details of the problem domains will only be touched on at a high level. And to finish, I will close with a few examples that we have deployed for customers. Here are the main 3 questions that I ask every time I formulate an RL problem. Question 1. What information do I have? Start by asking, what is the decision that I'm trying to optimize? And then work backwards to how the people in the organization currently make this decision now. What data sources are they looking at? Are they looking at the news? Are they looking at telemetry? Also, what variables of my system do my actions influence? Question 2. How many decisions do I have to make to finish the task? Many deep RL algorithms will evaluate the goodness of an action by assigning credit to it many steps into the future. This is a scenario where you need to keep interacting with the environment and continuously push it towards a desired goal state. Imagine that you are sitting in a log cabin with a wood stove and it's cold outside. You need to continuously regulate the room temperature by adding wood to the stove. There isn't any real end to this process, and the temperature inside the cabin evolves as you add wood throughout the day. These types of scenarios are difficult to learn and require something called a transition model that you need to learn from the data. There is a simple trick though, where if you just try and optimize the next immediate reward and don't worry about the rewards thereafter, then it simplifies the mathematics a lot and speeds up learning. You can find these simplified scenarios in many web applications. Like if a user gets shown an ad, they either click or not. If they get offered a price, they either buy or not. You get an immediate response, and you can train a model to predict the response, such as a click-through rate, directly. This choice of immediate versus long-term reward will impact how we build our simulation. We will get into a few examples in the next section. My final question. Is my algorithm learning anything? What does good look like here? Is there a target or goal state? And how is the organization calculating the performance of what they're doing at the moment? You need to be able to calculate a baseline on historic data. RL algorithms are complicated, and initially it is good to think of them as black boxes or even APIs. You will, of course, eventually learn how they work and how to tune them. You need to learn how to evaluate the training curves and always set a baseline and use it to compare the performance of multiple RL algorithms. I want to explore a problem that's in production now. A real customer operates these energy-efficient buildings in a cold climate area. They circulate hot water through radiant heat circuits under the floor of each room, and these buildings have telemetry, and all the rooms have existing control systems to control the temperature of the returning cold water. The controller in each room is regulated by a set point that is manually set by an operator. Only a small portion of these rooms have their internal temperature measured, so it isn't possible to control the temperature of the rooms directly. Currently, Operators manually adjust these set points many times a day to account for changes to the weather and occupancy. With this use case, we're in A/B testing now, and we expect to reduce this customer's energy footprint by about 20%. I'm going to walk through this example, showing you how to take offline data and build a simulator that can be run on SageMaker RL. Let's start with a process diagram of the heating network. The primary side of the circuit is fed by hot water from the power company. It goes into a heat exchanger and is distributed to the different rooms on the secondary side. Water is circulated under the floor of each room, and there is a controller that adjusts the flow rate of water to keep the return water temperature close to its set point. The lower the set point, the more heat energy we transfer into the room. An operator currently changes the set point manually many times a day to account for changes in external weather, occupancy, and supply temperature. We want to automate this. Let's practice our 3 questions. What information do I have? Here's our historic data. We can see that we have external weather measurements, internal room temperatures, and supply water temperatures. Which of these will react if we change our return water set point? Out of all of these, we can see that we can only directly influence our room temperature. Everything else, like the weather conditions and the supply water temperature, is out of our control. We still need these values, but they'll be treated more like historic information rather than a state that we can influence. We also transform the timestamp into features that help our models account for occupancy, solar radiation, and season. So, how is my algorithm going to solve this problem? And what is the measure of success? We can define one here. You can split the costs you give to an overheated room versus an underheated room by using a quantile loss function. And this is useful because a cold tenant might be more of a problem than a warm tenant during the winter. How many decisions are needed to solve this problem? This problem has no end. You can keep making changes to the return water set point, and then the system evolves over time. To understand how the room temperature evolves, we need a special function called to predict the future given the current information and the action. It's called a transition function. This function is going to give you the next predicted room temperature, given our current room temperature, our weather, and our return temperature set point. Because the system reaches equilibrium within the hour, the transition function can learn the next temperature directly. If this isn't the case, the transition function would have to learn the change in the temperature or its derivative instead. Here, we train a model and evaluate its performance over the test set. We then embed our model in an OpenAI Gym environment. We use the transition model here, and we perform an action every hour. We then calculate our costs here as well. Here, we test the fidelity of the simulator by passing in historic actions and compare the historic room temperatures against the simulated room temperatures. Here, we have an expert operator giving us a demonstration, and we then take the opportunity to capture a baseline. We then package our simulator within a SageMaker Docker container. We run 2 different models. Here we try DDPG and SAC. Let's look at the live training results of DDPG. The algorithm converges to a solution quickly, but we aren't beating our baseline set by the expert operator. Let's take a look at the live results of SAC. The algorithm is doing slightly better than DDPG, but we're still not beating our expert operator's baseline. It's not as good as the expert operator's baseline, but it can still keep the room to within 1.5 centigrade of the set point, without any human intervention. Looks like we could use a little bit more tuning or even a different RL algorithm. Might be a good exercise to try SageMaker RL parameter tuning. In the demo, we saw an expert demonstration, which isn't the case at all. In practice, operators are spread thin and there are fewer set point changes daily. Here, we baseline the performance of a typical operator, and you can see that the operator performs fewer changes. You can see small, sharp peaks, which are temperature changes due to occupancy. You can also see 2 gradual peaks, which are temperature changes due to external factors. All these peaks mean wasted heat and is an opportunity to optimize. The customer also wanted traditional optimization methods, so we also baseline supervised learning algorithms with optimization. You can see that these do a better job than the typical operator in the room tested. Here is the performance of the RL algorithms. The results here are promising and provide the most stable room temperature. The RL does a better job than the supervised learning because it tries to optimize the future reward, whereas the supervised learning with optimization uses the set point that it yielded the best result in the past. We are waiting for the end of the heating season to finalize our results with this use case. Here we have an airline customer that would like to make higher revenues by moving from a fixed price strategy to one that makes use of the fact that passengers are willing to pay more money during peak season. The airline can also make revenue by transporting freight. Here, we are operating a daily flight between two locations. We sell tickets through a website where a daily price is set. We get about 1,000 users on the website daily, and at the end of the day, the estimated weight of the passengers and the baggage allowance is allocated for. The remaining baggage capacity is allotted for freight. Let's practice our 3 questions here again. So what is the information that we have at hand? We have the rate for freight and the week of the year. How many decisions are needed to solve this problem? Let's use the trick of optimizing only the next immediate reward. So in this case, we make a single decision on daily price and then directly measure the revenue we've made at the end of the day. We don't need a transition model here because we aren't performing multiple actions that evolve our states. We use a simpler model that gives us the user's propensity to buy given a price and the season. We use some historic data fitted to a sigmoid model to estimate user propensity. We have our simulation like the previous example. Here's our propensity to buy function, and we use it to bias a coin that we flip to simulate a buy decision from the site visitors one at a time. We simulate 1,000 visitors over 1,000 days. Because there's no expert demonstration here, we select random prices each day to generate a random baseline. Is my algorithm learning anything? Yes, it is. Here's our baseline in red. We can see that 2 of the algorithms that we've chosen do fairly well, and these perform above the baseline that we've set. A real customer has an existing inventory control system and a forecasting model that they like. The products that they sell are obsolete within a year. They also do a reconciliation of their stock once a week. The supply and operations planning team have noticed that they stock out of inventory quite frequently, and they want to prevent their customers from going to their competitors. They would like to know how much extra safety stock they need to minimize stockout events without overstocking too much, because they will have to liquidate whatever stock is left over. Here we have an inventory control system using a stocking level policy. We need to pick how many extra weeks of stock we need to compensate for the error in the forecasting model. We're trying to optimize the item coverage and the profit margin. To use a stocking level policy, you need to first estimate the number of periods you want to stock for. The periods that you want to stock for are the sum it takes for you to do your order planning, the order lead time, and the safety cover in weeks that you want to have. The stocking level is the sum of the forecast for that period, and then the amount that you order is the stocking level minus the inventory minus the orders that you currently have in place. We use a simple trend forecaster for this use case. We use a diffusion model to generate realistic demand profiles. We combine it with a seasonal factor to simulate the demand over the lifetime of the item. Let's practice our 3 questions again. What is the information that we have on hand? We know the demand that we expect over the product lifetime, and we also know the week of year. How many decisions are needed to solve this problem? Let's use the trick of optimizing only the next immediate reward. So in this case, we make a single decision on the number of weeks of safety stock at the beginning of the product's life. We don't need a transition model here because we aren't performing multiple actions that involve our states. We fix our demand potential and then simulate the stocking policy and calculate the margin and the coverage for the item over its life. We build a simulator that generates synthetic demand profiles for 1,000 random but similar products. We don't have an expert demonstrator here, so we generate random choices of safety weeks to use in our inventory control system. Our final question. Is my algorithm learning anything? Not too sure. The model in orange converges to a solution below our baseline, and the other algorithm just performs marginally better than our baseline, inconsistently. It's a good signal to try a few more algorithms on our use case. So far, we've looked at immediate versus long-term rewards, building transition functions from historic data, propensity and click-through models, and we've evaluated our learning curves. When starting off, use RL as black box models, and you will get a deeper understanding of them as you practice. Here are the algorithms I recommend you start off with for single and multi-step problems with both discrete and continuous actions. Discrete actions mean that the actions aren't related to each other, like with add recommendations, and continuous means that the actions are related to each other, like with dynamic pricing. Now that we've taken a look into formulating the problem, I want to share my 4 steps to validate and test RL algorithms in production. This is the main focus of today's talk. Step 1. Try and understand the problem domain from the subject matter's expert's perspective. You have to articulate the actions that you want to optimize concretely. You also need to be able to define a measure on historic data. You can then use this as a baseline for the project. If we need to optimize the rewards over a long time horizon with evolving states, we need to learn a reward measure and a good transition function from our historic data. We then throw our data away and embed our transition function and reward measure into our simulator. If we use the trick of optimizing the next immediate reward, then we can skip the transition function and use simpler learning algorithms. Once we have a simulator, we can test historic actions and see how the simulator reacts. We can also sense check the actions being proposed with the SMEs. Try the RL algorithms that suit your problem formulation. You can use the distributed training and hyperparameter tuning in SageMaker RL to save you time. This is also time to try modifications to your reward function to improve the agent's behavior. When putting these algorithms into production, phase the changes into the business slowly. Start on a small subset of the population. Test its performance against the baselines you've captured, and you may need an operator in the loop to execute actions in safety-critical applications. Here's what we've helped our customers to do with RL. Our customer here wanted to improve on drilling costs by extending conservative rules of thumb for well cleaning while drilling by using rig floor measurements. We used reinforcement learning to recommend the action that improved the rate of penetration given historic drilling logs from that area. Building a transition model here was impractical because you're always intercepting new formations. And we used a Gaussian process model to build a custom bandit that optimized for drilling the next 100 feet. As you drill a horizontal well, you need to continually reduce the friction between the open hole and your drill pipe. Friction causes a reduction in your drilling rates. Typically, you have rules of thumb that recommend an activity such as cleaning every 400 feet or to pull the drill string back every 100 feet to keep it from coiling up. This delays you initially, but overall increases your penetration rates. We used RL to tell us what activity to do given rig floor measurements of weight on bit and circulation rates. There were 3 actions to recommend: keep drilling, clean up, and remove solids, and finally pull back on the drill string. The way we formulated the problem was to perform an action that improved the drilling rates for the immediate 100-foot section. Artificial lift is a very common application of RL. You need these systems to lift fluid from wells once the energy in the reservoir is depleted. There are approximately 2 million artificial lift systems worldwide. Oil companies spend millions of dollars trying to maintain and optimize these systems. Our customers have varying requirements in this space, but the general pattern is the same. We use reservoir models to decline the energy, like in a simple tank. This forms the basis of our simulator. We add equipment degradation models and combine this with wellhead control behavior and set points. Finally, we train deep RL models to optimize the set points for both maintenance costs and accelerated production. Existing artificial lift controllers are not that optimal. They use old rules of thumb and sometimes use first principle engineering assumptions. Recommending set points is a great way to make use of existing SCADA controllers and networks without the pain of edge deployments on secure industrial networks. We deal with multiple lift types in production, and we've used RL to recommend set point changes such as min-max speed ranges and gas injection rates. You can also take it a step further and use it to recommend the next design configuration. Our client, a gaming company, wanted to use RL to improve user experience around game level difficulty. They used a game engine called Unity and explored 2 RL algorithms available at the time on a custom EC2 setup. They wanted to try more algorithms faster and in a hands-off manner. We gave them a state-of-the-art distributed workflow on RLlib in SageMaker RL. In our benchmarks, distributed training can save about 20% in training time when compared to EC2. These models take days to train, so 20% is a big difference. So in production, we used an algorithm called PPO with convolutional neural networks to learn the game. Tune into Tokyo Summit for a deeper dive. We use RL as an unbiased game tester. Once the initial agent is trained, we looked at a number of times it's able to clear a stage configuration. The clearance rate is the difficulty of the level. I bet you can't wait to try some RL for yourself. We have many examples here to get you started. You joined the AWS Summit to learn, and you can keep the learning going after Summit with resources from AWS training and certification. For more information, visit the link below. Thanks for watching, and that concludes my presentation. I would love your feedback, so please fill out the survey for this session.